guess I actually go into go into the next section a little bit. This is 5.4. This condition is condition of a self-adjoint operator or Hermitian operator. Right? And this was, um, the property of the adjoint operator or Hermitian operator that we'll talk about that, in the next chapter about, I think it's about eigenvalue problem. There are more important property of self-adjoint Hermitian operator. Okay, and but the one property that in this section talk about is uh, uh, if this operator operate on suppose let me define a space. I guess we get rid of this. And the property is that you want to calculate the scalar product of psi and the A of this. Right? And for a Hermitian operator A, you want to see what this looks like, right? And obviously, then we can do a matrix, a basis expansion of psi, both psi and A. And now for this psi, you can see some of the new C set new by new. So that's the expansion of chi of psi and then A. And some for mu, C set mu by mu. Right? And I mean, I think actually before you do that, you have an operator. And you need a sandwich between this and that. Actually, it becomes the matrix element. Because, right? Some of them new, some of them new. You have C new. This is on the left. So it's compact conjugate. C new, and then new. That becomes the matrix element. Right? This is A mu, new. And then new, C new, A new mu. This is right. So this is this object. All right. And now we want to see that this actually is a real number, and the property of a Hermitian matrix is that they satisfy this one. So we can to see whether it's a real number, we can check the complex conjugate of this one. Complex conjugate. Some mu. And then C mu, they take the complex conjugate, this one, get rid of the complex conjugate, and C mu conjugate, mu complex conjugate, right? And now you use the property that that this or this A is Hermitian, so meaning you can A new mu, so I just erase that. A new mu is just A complex conjugate, right? This is the definition of Hermitian. So we can now get rid of this by exchanging the mu and mu. Mu, C mu, complex conjugate A, mu, mu. Right. So we got this line. And to see whether this is that, all we need to do is exchanging mu and mu, because these are just dummy summation. We can call them whatever we want. So if we exchange mu and mu, it doesn't matter. The double summation doesn't matter. We can just C mu or C mu, C mu. Now you compare this with that. This is exactly the same. This is okay. So you see that the compact conjugate of this object is equals to itself. It means that we are real. Okay, so that is straightforward. And so that one property of dimension operator, and that make it important in the sense of applying to physics, particularly quantum mechanics, because if you treat all the dynamical variable as Hermitian operator, and this object between state, this psi become what we call the state of whatever your quantum system, your quantum state, and this object is what we call the expectation value of the operator, that sandwich between the same state. And obviously, if A is represent real physical quantity, the expectation value you must you must expect that to be real. You like measure the whatever you want to measure, the distance or whatever, the electric field or whatever. Like you expect them to be real. So uh, so this property is saying that the Hermitian operator sandwich between the vector will give you the expectation value will be a real number, and that is important, right? So that therefore you have the assumption that all this dynamic world, real dynamic world, where you can make measurement and get a number out. When you do a measurement in the real world, you're not expecting to get a complex number out. So you expect to get something real. So therefore, the operator must be Hermitian operator. Okay, so that's that's property. Let's turn left. All right. See that example. Self-Adjoint operator. Okay, this one is, I think it's the same as the other one. This minus IDDX is self-adjoint. I think that using the same integration by part, you can see that is self-adjoint. That is what is proportional to the momentum operator that in quantum mechanics, except that you need to multiply by h bar. I think the rest of the example, let me just 4.3 is operated. I mean, it's just how you manipulate operator on using the adjoint definition, which is straightforward. So whether you want to operate on the left or on the right, you can use the adjoint operation. And now for Hermitian operator, it's straightforward. Whether they operate on the left or the right is the same, because the adjoint is the same operator. It means this one, if it's not psi, you consider psi. Just like when you test it, you can operate on the right using A. If A is Hermitian, you can also operate on the left, right? And that's the property of the Hermitian operator, right? And that takes forward. Yes. Yeah, I think there's one topic that talk about functional operating. Right? And this is like what I think I mentioned, that the function of matrix. Sometimes we have a function of matrix also. So you get FA. put a operator in a function A, then the way to do it is to do a Taylor expansion. Whatever that the Taylor expansion of this function f is the sum of n into infinity. You have this coefficient, which is in this n derivative, and then a is n. Right? We use this definition. It means the sum of all the terms, and each term has a different number of products of the A with itself. And in this case, it's trivial because A commute with itself, so that there's no problem with order. And the string property is that this power expansion, if you have involving two operator, and the order of this power, like A M B N, A B A M B N, that the order becomes important, and that is all the difficulty. If you have like a multiplied by FA with G, B, right, and that that even if the two functions are the same, so like exponential function of A, exponential function of B, that is usually not equals to exponential. I mean, usually for number you have E A plus B, right? That the operator is not the same because of this this non-commute. If A and B, if this is A and B, not commute, not this, right? Then the sum of the property of a function that we are so familiar cannot be carried to function of operator. That you need to be a little careful. We talk about functional operator. Right. I think that's all for 4.4 self-adjoint operator.